Welcome to The Explainer. Today, we're diving into something that literally feels ripped straight out of a sci-fi novel, but is actually happening right now in research labs. We're talking about artificial intelligence decoding human brainwaves, translating our private thoughts into text, and recreating the images we see in our mind's eye. And honestly, the most incredible part, they're doing this completely non-invasively. No surgery, no implants, nothing like that. So, can artificial intelligence actually read your mind? It's a question that probably sparks a mix of absolute wonder and, yeah, let's be honest, a little bit of anxiety. For decades, this was purely the realm of fantasy. But thanks to massive leaps in machine learning and neuroscience, that barrier is finally beginning to crack. In this explainer, we're going to look at the exact science making this possible and pull back the curtain on what looks like a magic trick. Here is our roadmap for today. We'll cover the era of mind reading, translating thoughts into text, visualizing the mind's eye, mapping the visual brain, horizons in assistive technology, and finally, protecting your mental privacy. Let's get right into it. Section 1. The era of mind reading and non-invasive brain decoding. To understand how researchers at UT Austin and Osaka University are pulling this off without a scalpel, we've got to talk about fMRI, or functional magnetic resonance imaging. Unlike an EEG that measures those rapid electrical pulses on your scalp, an fMRI tracks much slower changes in blood oxygen levels. Scientists call these bold signals. Basically, when a part of your brain works hard, blood rushes to it. Because the fMRI tracks that blood flow, researchers can map your brain activity with stunning precision, all completely non-invasively. Moving on to Section 2, translating thoughts into text using the UT Austin Semantic Decoder. So researchers Jerry Tang and Alex Huth at UT Austin wanted to see if they could translate brain activity into a continuous stream of text. To do this, they matched fMRI patterns with GPT-1, an early version of the AI behind ChatGPT. They had people listen to stories or even just silently imagine telling one while in the scanner. Now, look at this comparison. The person heard the words, "I don't have my driver's license yet," but the AI decoded it as, "She has not even started to learn to drive yet." It's fascinating, right? The AI acts as a semantic translator. Since blood flow changes slowly, it's not grabbing a literal word-for-word transcript. Instead, it captures the continuous gist, or the core meaning of your thoughts. And what's truly staggering here is the efficiency. Older brain-computer interfaces used to require dozens of hours of training data for just one person. But this new algorithm, it adapts incredibly fast. A new user just lies in the scanner, watches silent videos, like Pixar shorts, for about 1 hour. That's it. In just 60 minutes, the algorithm aligns the new user's unique brain blood flow patterns with the pre-trained AI model. All right, Section 3, visualizing the mind's eye and recreating images with stable diffusion. Okay, so we can decode the gist of a thought into text, but what about visuals? Well, a team at Osaka University actually managed to recreate high-resolution visual experiences straight from fMRI data. Instead of words, they translated brain activity into pictures. To do this, they built a visual reconstructor utilizing stable diffusion, which is a super popular AI that generates images from text and data. But here's the real genius of it. They didn't spend millions of dollars retraining this massive, complex AI from scratch to understand brainwaves. Nope, they just used simple, linear models to build a bridge, seamlessly mapping specific human brain regions directly to specific parts of the Stable Diffusion software. Which brings us to Section 4, mapping the visual brain and how anatomy meets algorithm. This is where the science gets absolutely beautiful. The researchers mapped human biological brain anatomy directly onto the AI's digital architecture. Think about it. When you look at a picture, blood flows to different parts of your brain for very different reasons. Your temporal lobe handles the contents and meaning, like, oh, that's a person or that's a car. The researchers mapped this straight to the AI's clip text embedding component, which handles image conditioning. Meanwhile, your occipital lobe processes dimensional layout, perspective, and scale. So they mapped that to Stable Diffusion's latent space, which is basically the mathematical area where the AI figures out the spatial layout of an image. So let's put it all together and walk through exactly how a thought becomes a digital image. Imagine someone is in an fMRI scan looking at a photo of a clock tower. Step 1. The fMRI scans the blood flow in their occipital and temporal lobes. Step 2, the semantic meaning from the temporal lobe, that clock tower concept, is fed into the AI's text generator. Step 3, the layout and perspective from the occipital lobe go right into the AI's spatial generator. Finally, step 4, the stable diffusion model merges those inputs together to generate a photorealistic digital picture of the exact clock tower the person is looking at. It is just wild. Section 5, Horizons in Assistive Technology and Moving Beyond the Sci-Fi Novelty. We definitely need to pivot from the cool sci-fi aspect of this to the profound real-world human impact. Because this isn't just about reading minds for fun. It's about therapeutic applications that could fundamentally change lives. For instance, there are 1 million people in the US alone living with aphasia, a neurological disorder that impairs language. Add in stroke survivors and patients with ALS or locked-in syndrome, and you have a massive population of fully conscious thinking people who are trapped inside their own bodies, completely unable to communicate. This non-invasive decoding tech offers a genuine path for them to regain their voice and interact with the world again. Now, you might be thinking, okay, but people can't exactly carry around a multi-million-dollar room-sized fMRI machine to talk to their families. And you'd be absolutely right. But the UT Austin team has pointed out a really exciting path forward for mobility. Future portable brain-computer interfaces could rely on something called FNIRS, or functional near-infrared spectroscopy. Basically, FNIRS can be worn like a simple cap on the head, and it measures the exact same blood flow signals as an fMRI, just at a slightly lower resolution. This totally points toward a mobile, wearable future for this kind of technology. Finally, Section 6, Protecting Your Mental Privacy and the Ethical Guardrails. We absolutely cannot talk about extracting thoughts without addressing the elephant in the room, your mental privacy. The idea of mind reading naturally brings up some pretty heavy fears about unauthorized data collection. But let's look at the hard science here, because there are some very strict limitations acting as built-in guardrails. First off, decoding only works with a willing, cooperative person who's undergone the specific training. If you resist just by actively thinking about something else, like counting numbers or imagining a different story, the AI's output instantly degrades into total gibberish. On top of that, our brain patterns are incredibly unique. If you train a model on one person's brain and then try to use it on someone else, it just spits out complete nonsense. So from a purely scientific standpoint, covert unauthorized mind reading is literally impossible right now. And I think this quote from UT Austin researcher Jerry Tang really hammers home the philosophy here. He says, "We want to make sure people only use these types of technologies when they want to, and that it helps them." Ethical cooperation isn't just some nice idea tacked on at the end. It is quite literally woven into the mathematical fabric of how these AI models function. They require your consent to calibrate, and they absolutely require your ongoing cooperation to even operate. Wow, we've covered a tremendous amount of ground today. We've seen how blood flow, neural anatomy, and AI architectures are all converging to decode the language and the images right inside our heads. It's a massive leap forward that promises to give a voice back to those who have lost it. But I want to leave you with this provocative thought to chew on. As AI continues to unlock the secrets of our internal visual and semantic experiences, what will we ultimately discover about how each of us uniquely perceives the world? Thanks for joining me for this explainer, and keep pondering that incredible frontier of the human mind.